Good afternoon and welcome to our webinar. My name is Wes Saunders and I'm joined today by Todd Roberts, the Director of Infrastructure at Sensemetrics. In our presentation, we're going to highlight a case study on the instrumentation monitoring solution and database management for the Finch West LRT project. A couple of notes to start. If you have any questions, please submit them in the questions sidebar. At the end of the presentation, we have allowed for up to 20 minutes to address as many questions as possible. For any questions that we're unable to answer, we'll be responding offline. And should you have any questions that you wish to ask privately, certainly please don't hesitate to email us directly. So a little bit about our backgrounds. I'm a professional engineer in the province of Ontario and have worked in the field of civil engineering for 14 years. The first 8 years was mostly with DST Consulting Engineers in Thunder Bay as part of their geotechnical team, focusing on soil investigations as well as foundation and embankment design. Then for the last 6 years, I've been working with GKM as a project and business development manager, where our focus is dedicated specifically to the geotechnical and structural instrumentation and monitoring. Todd?
Thanks, Wes. Again, I'm Todd Roberts. I work for Sensemetrics based in Denver, Colorado. Much like Wes, I have a lot of industry experience, 20 years of which have been in the geotechnical space. Of those 20 years, 15 years was practicing as a geotechnical engineer and geologist, where I was able to build an instrumentation team that focused on delivery of design and monitoring services. The last 5 years of my career have been focused on the manufacturing side of the industry, and currently I'm at Sensemetrics managing the infrastructure team. So now we're going to turn the presentation back over to Wes.
In our presentation, we will provide a brief overview of the project background, some of the instrumentation that's being used, challenges that have been necessary to overcome, and some of the solutions we have looked for. I will then pass to Todd such that he can provide some of the details on the Sensemetrics platform, after which I will go back and highlight some of our approach to data visualization, which is being used, the installations we've completed, and a couple of lessons that we can take from the project so far. Finally, as I mentioned previously, we'll have a question period to close out. So a quick introduction about GKM. We're a multidisciplinary group of engineers and technicians headquartered in the Montreal area with backgrounds in civil, mining, electrical, and environmental sectors. Our focus is to serve as an integrator to our clients who can provide custom instrumentation and monitoring solutions. This includes assistance in selecting the appropriate hardware, managing procurement, completing sensor installation, as well as management of the instrument database. This approach has allowed us the opportunity to work on some of the major infrastructure projects that are currently occurring in Canada and around the world.
So now we're going to do the same overview for Sensemetrics. While operating on 4 continents, Sensemetrics has physical offices in San Diego, California, where we're headquartered, as well as in Denver, Colorado, where I'm based. I'm also joined by my colleague, Nate McGee here, who runs our technical services department for the company, and he'll be helping out throughout this presentation with questions primarily. Both offices team up to continuously develop and maintain our hardware and software offerings. Sensemetrics is commonly regarded as an emerging standard in the monitoring space, where we work in many verticals ranging from transportation, like the Finch West project we're talking about here today. We also operate in the water resources industries, mining, construction, energy, and oil and gas. We have a strong global network of partners where Sensemetrics provides various monitoring solutions to hundreds of owners, operators, engineers, and consultants, and we've hosted over 300 million observations to date.
So the Finch West LRT project is a light rail expansion project in the Toronto area, and it's part of a larger transportation network expansion that's occurring in the region. The P3 team for this project consists of the owner, Metrolinx, operator, Toronto Transit Commission, and the design build group, Mosaic Transit Group, which is a consortium of major constructors operating in the region. The extension is 11 kilometers in length roughly and includes 16 surface stops with 2 underground stations. One is a terminus at Humber College, and the second is the interchange link which joins this section of line with the Toronto York Spadina extension. Additionally, the project will renew some of the aging infrastructure along the corridor, such as the Highway 400 overpass, as well as a number of creek crossings. The geotechnical instrumentation and monitoring component of this work has been awarded to Acrivis Instrumentation and Monitoring, also known as AIM, to who GKM is providing support for the necessary automated data acquisition systems, instrumentation sensors, and database management. So this scope of work includes monitoring of the critical project infrastructure, such as existing buildings and utilities for movement, as well as the response of environmental conditions to construction activities. Altogether, we're looking at over 1,200 individual monitoring points from various automated and manual instruments. When working with a large quantity of sensors such as this, there's always many different technologies and monitoring approaches that need to be integrated. In particular, we're managing a combination of automated sensors using both vibrating wire and MEMS technologies. These include Geocon's multi-point borehole extensometers, piezometers, strain gauges, pressure cells, load sensing's biaxial tilt meters, as well as Measuran's shape arrays. On top of these automated sensors, there's also a significant number of readings from total station measurements, inclinometer surveys, and water standpipe measurements, all of which we're integrating into the visualization platform. So in integrating these instruments and technologies, one of the challenges has been to maintain flexibility in the design such that it can adapt to the conditions along the route without driving up costs. So in planning for monitoring the 12 specific construction locations that include both above and below ground structures, active rail and vehicle traffic, as well as areas open to the public, we needed a system that could manage multiple communication technologies. We also needed to accomplish an efficient installation and required a system that was fairly simple to set up, could be deployed in a short period of time, and would cause really as little disturbance as possible to the site. We also needed to consider how we were going to manage a large data set and accurately convey critical information to all of the involved parties. This required a method that was capable of managing over 1 million readings over the duration of the project while providing meaningful alarms to the project teams.
Wes, looking at this photo here, for the audience benefit, what was some of the instrumentation challenges with getting access to a busy subway environment?
Well, this existing station was active during the regular hours of operation, but we were able to access the concourse and platform areas during the night shift, and then we had approximately a 3-hour window to complete any of the track work.
Okay, thank you.
So to achieve as many of these objectives as possible, we chose to focus on a combined system which uses load sensing's LoRa hardware as well as Sensometrics thread hardware, and this was to integrate the data into the Sensometrics visualization platform. The load sensing hardware uses a battery-powered data logger nodes connected to wireless gateways through a long-range, low-power wireless protocol. And we have found that the LoRa system has been quite powerful in both above and below ground applications. In urban environments, we've successfully transferred data over 1 kilometer in distance, and that's used with post-mounted antennas, as well as several hundred meters from the gateway when installed in flush-mounted well protectors fitted with an auxiliary road-rated antenna. On top, the Sensometrics platform has proven to be very adaptable to our work scope, and it's been very easy to integrate the multiple technologies and clearly convey the large data set while allowing multiple parties to prepare visualizations really as they see fit. So here I'll pass to Todd to provide an introduction and insight into the function of the platform.
Thanks, Wes. So I'm going to take a few slides here to walk the audience through what our platform consists of, to put it in perspective before Wes takes on some of the case study pictures and data sets that have been collected so far. So the Sensometrics platform consists of an integrated hardware and software pairing. It delivers a true end-to-end solution by integrating a wide range of sensors into a single software environment. Sensometrics offers everything from plug-and-play connectivity on the left to sensors, as well as device controls such as vibrating wire interfaces to data management, all on a secure cloud-based platform. In addition, the analytical engine delivers software solutions that allow users to engage in various functionality set ranging from reporting module, analysis tools, and or even more advanced software features that we call productivity applications, depending on the project needs. Wes will walk us through some examples of many of these feature sets as we go through the presentation. In order to deliver this seamless experience for monitoring, SenseMetrics aligned with many industry-leading sensor manufacturers shown here. This allows the owner and his engineering team to design and deliver a monitoring program that is optimized to project objectives. For Finch West LRT, GKM relied on many sensor types that Wes previously has described, such as vibrating wire and MEMS sensor technologies that are manufactured by companies like Geocon, Measurand, and a couple others. This strong partner network also enables projects to quickly adjust to changing project conditions by adding pre-supported sensors into an otherwise unforeseen design phase, and allows to quickly adopt and pull those new sensor types in depending on project challenges. Examples of how some of the integrations work. Here we're looking at load sensing devices, GKM's wireless nodes that automate directly to SenseMetrics platform using their gateway devices. And a gateway device is any internet connected device that lands these sensors, the connected sensors, into the software. Alternatively, GKM relied upon Measurand shape array sensors for deformation monitoring that will be automated, powered, and controlled using SenseMetrics threads. There's the white box with the green SenseMetrics logo on it shown here. Example of this integration is the thread is able to pull the serial number off the shape array. SenseMetrics platform then accesses Measurand's office in Canada to pull the associated calibration information for immediate upload in the SenseMetrics platform. From the time you plug in the shape array and the thread, you have seconds before the automatic calibration is completed in SenseMetrics. Other examples of more complex integrations would be geospatial monitoring using automated motorized total stations, or also called robotic total stations, to acquire 3D deformation metrics over a distributed prism network. On this slide, we'll see a Leica TM50 series robotic total station that's powered and controlled by a thread. And Wes will talk about throughout this presentation the difference between manually collected survey prisms versus automated prisms that we hope to deliver on later on this project. On the software side of things, GKM accesses sensor data using what we call as our core applications shown on the left here in the green icons. Wes will show examples of this later, but I want to give you an overview of the software features that are available to all the authorized users. On the top left here, you'll see the Maps module. This is basically a GIS interface that allows users to create a single or layered top-down view of the project. Maps module also offers the ability to upload images such as photographs, CAD drawings, and even cross-sections where the user can co-locate sensor icons. On the graphing tool, you have the ability to create single or multi-parameter time series graphs sourced from one or more sensors and or sensor types. An example of this would be pairing, let's say, piezometric data with rainfall data and then graphing them against downhole deformation to create cause and effect relationships. The core applications, as we call it, also allow for single or multiple alert levels. Wes will climb into this in more detail soon. And we're also able to provide access to data tables, which supports import and export functionalities. On this screen here, we also have additional software features that we call productivity applications, shown in blue here. For example, GKM is relying a lot on the report module, which we'll dive into more later. This creates auto-generated reports that prepare a PDF document that's delivered on a scheduled method. And Wes will give us examples of all this stuff later on. So now that we went through sort of a high-end overview of SenseMetrics, I'm going to hand it back over to Wes here.
Thank you, Todd. Now I'll kind of pass through a couple of examples on how we're representing the data on this project. Now, please keep in mind, this is a representation of the data and not exactly what's being provided. So for the general overview of the project, we have currently utilized the Spatial Maps page, which allows the presentation of all the points on either a georeferenced map or a user-defined map. Here, this is an example where it's shown with an ArcGIS topographic map. Now, we've found this to provide a good balance of information while being easy to navigate without creating too much clutter on the screen. There are also many features that can be used in this view, such as icon coloring. You can see here that they're green, where this indicates a positive connectivity. But in a condition where maybe you had a gateway go down or you had some nodes that for some reason weren't communicating properly, this status would turn to red and allow you to identify specific areas of interest. In addition to this, there's also a function for alert flashers. So anything that is approached, any of the triggers or alarms that you've set would show with a flashing halo around the icon. So in addition to that, a couple other, I'll say, features that you can utilize where you're dragging over the sensor icon. You can pull up graphing data as well as some of the latest readings that may have occurred on that location. Another representation that we tend to use is a site-specific drawing to augment the global map. Here we can use location and instrument-specific drawings that'll highlight a group of sensors and provide a more detailed view. This example here just shows a number of biaxial tilt meters and electro levels, but as the project will progress, you can add functions like multi-point borehole extensometers or shape arrays to combine the different sensor types. Next, let's look at some of the graphing modules. Here we have a combination of summary profiles that look at a group of sensors of a particular type or installed at a particular location. This is an example of some biaxial tilt meters on a time series plot. Now, this is a very basic example, but it's quite simple, just using the plus icon on the left where you can add or remove additional plots. And so this has allowed us to easily create displays that are showing the movement along with other influencing factors such as open standpipe water levels or strut strain in an earth support system or earth pressure on the back of tunnel liners. And these can all be combined together.
Wes, this is kind of giving the audience an example of what Sensemetrics calls profiles look like, and you can, as you said, make different custom views. Can you please elaborate on the rough number of users and companies that are accessing these profiles for the project?
So far on this one, we have approximately 20 users that are based over 5 companies. Now, in that group, you have many different types of users. So one we define as super users, and they would be assigned an individual access name, and they would be able to go through and edit different panels and profiles and really create the platform how they see fit. And others would be view only, where it's more of a group entry point, and that could be shared between multiple parties in the organization.
Okay, great, thank you.
For presenting the shape array data, it's much easier to look at in an XY plot. A couple of features that we certainly appreciate here is the ability to select it's called a rolling data interval. This allows us to record data at a higher frequency than it is shown in the plot, as well as make adjustments to the number of readings that are presented. Now, this provides a high quality data set that you can export when you need to complete a detailed analysis of the movements that are occurring over, say, a daily, weekly, or monthly period, but maintains a graph that is easy to view and can convey movements over a longer period of time. Also, as we've seen with many of the shape instruments, the ability to link or adjust the baseline is right within the plot. And this can really allow for simple correction due to unforeseen disturbances on our sites. I think many of us know that instruments can become targets or can accidentally be disturbed during the construction process. So it's a handy function to have closely available. Now, when setting up or preparing alarms for the specific sensors, we have a couple of options on how we like to set up. Now, typically, we like to choose the alarm priority, the sensors to which it applies to, as well as a handful of triggering criteria. So for an example, let's consider a biaxial tilt meter. We would set up during the baseline and collect as many readings as it is practically possible. From this, we would take a look at the recorded range and compare it to the expected range that was provided by the designers. And then from this information, we would start defining our alert levels. So, for example, should we consider a review level? Perhaps it would be 125% or 150% of the experienced range during the baseline, and then maybe the action level is 200% of this range. Now, upon any exceedance of these conditions, we can trigger a series of actions ranging from alert notifications that are sent to specific team members or to the changing of measurement frequencies on specific sensor groups in the area. Options all actually even include the possibility of triggering a relay, which can display visual alarms on site or even activate a series of pumps. Now, typically we like to build our alarms in layers, such that you would see alarms that would trigger an additional data review, as well as an alarm that would trigger specific predefined site actions. Now, I just want to spend a little bit more time on here than the other data slides, because I think the alarms really hold great value and must be very carefully designed such that they don't create any unnecessary confusion. Two features here that have really helped reduce unexpected triggers are the options to set multiple rules that must be met, and another option is to have consecutive readings that are past the alarm value prior to triggering your alerts. This option allows for a much greater specificity of the cause of the alarm. However, they naturally must be used in appropriate circumstances. For reporting on the project, we're utilizing an automated report generation tool. We're currently generating a summary on a weekly basis, but really this can be defined at whatever frequency is necessary for your specific application. I believe that we may end up generating a couple of different reports at various stages of construction on this project, and it'll likely be a smaller summary report on a higher frequency basis, and then a larger, more detailed instrument review package on a lower frequency basis. Normally, for the short report, we'd include a summary of any of the alarm triggers at the forefront of the document, followed by a series of summary graphs. And then alternatively, for a full detailed report, we would go through and include copies of all the individual sensor graphs in the package. Now, this report function doesn't always need to be published to everyone within the project team. Specific work groups or teams may require a report for their own detailed information set. So as such, any user can go in and generate a profile that meets their specific needs or format for that purpose.
Hey, Wes, I have a question on this. I think a report module, will preface the question. Report module is a very common feature that our users use, and it's to generate auto-generated reports like you're describing here. If you weren't using the SenseMetrics report module, how long would it take GKM to prepare a similar report?
That's very dependent on the project, but let's say we're looking at manually creating plots from Excel or taking screenshot data from smaller reports. This can take, say, 4 to 8 hours, depending on the number of sensors and the complexity of the interactions that are occurring on site. But with this project, as it reaches full swing, the manual preparation, I think, of some of these packages could take many days, potentially an entire week of staff time.
Okay, thank you.
All right, moving from that, let's take a quick photo tour of one of the installations that we've completed. This is the existing underground station at Finch West, where GKM and AIM's team worked together to install 13 of the biaxial tilt meters and 16 tilt beams. So as I previously mentioned, to complete this install, our team only had access to 3-hour track windows, and therefore we really needed to be as efficient and coordinated in our efforts as possible when on site. As such, prior to the night of the physical installation, we did complete a couple of site visits. The first would be this center photo where we were there to test potential gateway locations. Now, we did this to ensure stable communication to the node locations, as well as the development of a reliable method to transfer out the data. Now, keep in mind that this is a public access area as well as it is architecturally finished. So we really needed to carefully consider where the installation can be safely completed, as well as where it would be allowed by the operations team. So from this, we determined that actually a single gateway located on either the concourse or the platform level would be sufficient to reach all of the installation locations in the station, as long as they were positioned appropriately and the antennas were set correctly. Next, on the left, you can see here our team members just setting up the hardware while waiting for our access to the track time. And then on the right, finally gaining the access and completing some of the installations. Next slide. Finally here, just a couple of photos from the finalized installations. Of course, we'd like to congratulate both the staff from AIM and GKM for their hard work and professional approach to completing the site, as well as to thank all of the staff from Mosaic and the P3 group in working with us to facilitate the installation. So I'd like to move to a couple of key lessons that we think are important to share from this project so far. First would be the influence that temperature can have on readings and how it can play a significant role. We have to keep in mind that the accuracy and resolution of these sensors is quite high. So we're able to see a resolution in recorded data as small as 1/1000th of a degree for our biaxial tilt meters. Now, for reference, this is 2/100ths of a millimeter of movement over 1 meter of reference length. So on this project, our experience has been that the variation in tunnel temperature between day and night can often be quite high. We've experienced changes of up to 10 to 15 degrees Celsius during the winter months. And this can influence our readings in three ways, really. The first of which actually can be lab calibrated, and that's the effect of the temperature on the performance of the sensor chip itself. But second is the thermal expansion and contraction of the mounting hardware for the instrument. And third is the associated movement with the structure. So as you can see, these factors lead to my next comment, which is the importance of careful selection of review and alert levels. With the ability to record readings with such repeatability at these high levels of, high levels of precision, it really can be possible to create alarm levels that are too strict and don't allow for the natural variation in readings that can come from multivariable problems such as this. So what we find is the best practice is to have as long of a baseline as practically possible, which experiences the majority of the natural occurring conditions prior to the introduction of constructions. This can help minimize the potential for misinterpretations of movements that are actually, say, biannual or seasonal movements. As I mentioned before, the data transfer can also be a challenge, specifically when you're 3 stories underground. It's important that all parties are aware of the potential limitations in using items like cell modems under these conditions. After our investigation, although we felt it was plausible to use a cellular modem, it was deemed best to utilize the existing network underground to push the data out, since we found significant limitations in the ability to do it reliably with the cell network. And this was specifically because of the required antenna cable lengths, as well as the available installation locations, just due to the potential modification of architectural features such that we could mount hardware or route cable. So ultimately, it was determined that best to really set our gateway up based on the existing data transfer infrastructure in place. Lastly, I think we believe that keeping the system open and adaptable to the changing construction environment is incredibly important. And one of the reasons this is the case is because the decisions that are made by integrators and providers such as GKM and Sensometrics, they're being made very early in the stages of development of the project. And so as the design matures and reaches completion, there's frequently the addition or substitution of sensors or sites. So we find great value in being able to add to the existing base instead of relying on a new and separate hardware at each change. So on this note, I'd like to thank you for your attention and open our question period. Todd, can you kick it off, please?
Sure, thanks, Wes. So we had a few pre-submitted questions sent in, so I'm just going to tackle a few of them directly here before we go to some of the live streaming questions that are coming in. I see Nate's working diligently on over here. One of the questions we got was how far is this platform from a digital twin? And that's a good question to start off with, because there's a couple questions that are related to that as well. The monitoring platform, the SenseMetrics platform alone is not quote unquote a digital twin, but rather a scaled down version focusing on the monitoring aspects of the LRT project. I think the important note here is that we are a piece of a bigger puzzle, the digital twin puzzle, where SenseMetrics can use our API, which is Application Programming Interface. For those that don't know, it's sort of a digital handshake between our software and somebody else's software that allows for sensor data to be passed on to a digital twin platform. There may be folks on this call that have experience with that, and so this question might resonate with many. Another related question is, how can the data be shared with the operations control room of the City of Toronto and first responders for crisis management? Another good question. We have options here, basically. Toronto and first responders can be given an account where they can log in and see real-time data. Alternatively, GKM can also export and download data and email it to them directly. A little lag time there, of course. Or perhaps another way of doing it would be some similar to the digital twin, where we can provide access to sensor data using our API, at which point the data can be integrated into the city's or first responders' workflows in a digital transformation space. So that those two questions kind of relate well to each other. Another question we have from an engineer is a multi-pronged question, so I'll read it off together here so you have the context. Are there real-time monitoring for this project? How automatic are they? What are the monitoring frequencies? And what are the monitoring accuracies? And so this is like a joint effort response here, so I'll kick it off. Basically SenseMetrics is what we consider to be near real-time. Real-time sort of a little bit of subjective, but near real-time is the right term to apply here. For perspective, many sensors can be read as frequently as every minute, but this is not common in practice, and in some cases generates a lot of data and becomes a burden on the user to have to sort through. That's where SenseMetrics platform comes in to help out with data management. The user also has the ability to manually adjust reading frequencies, so you can slide quickly from daily once-a-day readings to every 6 hours, to every hour, to every minute. You can also set up thresholds that trigger increased reading frequencies, as Wes was describing earlier. So you have the ability of automating the changing in reading frequencies. And then Wes, can you talk a little bit to the monitoring frequency for the project and the monitoring accuracy that was specified?
Certainly. So for this project, the bulk of the automated instruments are being read at a frequency of once per hour. This is proven to be fairly standard, and it's as Todd was mentioning, it's a good balance between having plenty of data for analyses in the sort of the time sphere that we're looking at for geotechnical and structural movements. And then for the accuracy, an example would be the tilt sensors, the MEMS chips today, the ones that we're using specifically, have an accuracy and a repeatability of 0.005 degrees when they're within plus or minus 5 degrees of vertical. So from that, I'll move to another couple questions that we've taken pre-existing here. The first was, what measures did we use to limit and account for instrument failure? Now, in this case, the hardware that we've been using has a fairly low failure rate. Our experience over the past 5 years has been actually less than 1%, but from our understanding, the industry standard that is targeted is to achieve a failure rate of less than 1 to 2%, really. So we've kind of been in that ballpark, and how we mitigate for that happening is we'll store a couple of additional units on site, or in the region, really, and that just helps reduce the response time and lag for shipping and processing of that nature. So we carry an extra gateway sort of nearby, as well as a couple of different nodes for each type of instrument that we have. Next, we'll look at a question on how do you define critical points to secure with monitoring? Now, that's very much dependent on the risk profile analysis that's done by the design team. So different areas of the project are going to be interpreted differently. If you're building something next to an empty parking lot, it's very much different than if you're building it next to a 5-story residential structure, which is also very different from building it next to a historic landmark that has been around for centuries. So you have to look at it in context, and you have to look at the risk. So each one's different, and it's going to be based on the structural conditions at that location, as well as the geotechnical factors that can be influenced from the construction. Todd, do you want to take a couple questions, please?
Sure. So let's pull some up here. Okay, so a question came in. Audience member would like to know about vibration control and structures during driven pile applications. Do we have experience with this application in the platform? The answer is yes, we do support vibration monitoring data in our platform. That's the short answer. There's not much more to say to that, I guess. Another question is, how is data being collected and used, and who is using it? And we'll say, what was another part of this question? Often the data is just collected and performance is not evaluated until something happens or a trigger is set off. Should we rely on a computer to monitor facilities, or should we include a human? This is a great question, and SenseMetrics is a tool to assist humans in monitoring applications. Basically, without SenseMetrics or automation techniques and automated devices like load sensing devices and other products that are available and threads, it is hard to manage 1,200 data points on an hourly basis. You would need an army of humans. But what if we could replace that experience with efficiencies and tools that enable for more efficient monitoring, where we can monitor 1,200 points in an hour? So SenseMetrics built a platform that caters to that experience, where we can take a lot of data and then automate it and funnel it into a single monitoring platform, where then the users then can set up alerts, manage distribution of data and who can see what access privileges different users have, so that the operators and the managers and the owners and the engineers and even the contractors can see the monitoring real time or near real time using a single platform. So that's a long answer to that question, but that was a very good question.
I think I have another kind of add-on to provide there too. Our experience has been that groups are pushing for higher and higher monitoring frequencies. So pushing it from, say, every 6 hours to every 4 hours to every 1 hour. Now people are trying to get data every minute. And really, the actual data collection and the data transfer isn't the limiting factor on responding to most of the situations that are arising. It's having skilled engineers that are able to efficiently review the data and then engage in predefined site action plans that have been laid out and bought into by all the parties that are participating in the project. It's that's really where we're seeing the biggest hurdle to overcome and optimizing the use of these sorts of platforms.
Yeah, automation doesn't remove humans, it just makes them more efficient and gives them the ability to react faster and make more informed decisions, basically.
Okay, I have a question here that I'll answer. It's relatively easy. So it was uploading the manual data. How are you doing it? So for example, there's, call it 900 survey points on this project. I know it's not an exact number, but roughly close. So we would take the survey data from the technicians, and you would parse it down into a comma-separated variable file that has details such as the sensor ID, the date and time, as well as your northing, eastings, and elevation, or if it's, say, a water standpipe, then you have your water level, or if it's a manual leveling point, just your elevation. And then there's an import page where you choose your CSV file, you make sure it's linked to all the right sensors that you've created in the platform, and click a button. And once you've gone through the setup, it's relatively seamless, and you can upload hundreds of points in a series of minutes.
Okay. How are we doing on time here? We got a few more minutes. We could take a question or two more, I think.
If you don't mind taking one, I just want to look through the ones that I have here.
Just looking through the questions here, guys. We're getting a lot of good questions coming in.
Here's one. For shared entry, is that a single username and password distributed to many people? Yes. So that is a case where you would create and say an email address, generic Finch West team at AIM or acrivis.ca. And so that email would be associated with a specific set of user rights, and then that would be used as a group. One of the challenges in having many users is each time you're setting up sort of profiles, you need to really determine who has access to view, who has access to edit. So as you add to the number of users on the system, it can become more cumbersome. That's why for those personnel that really aren't using the system on call it a daily or weekly basis, and they're just periodically checking into it, it's usually best to use a shared entry.
Okay. I think we're about nearly out of time, and I guess again, Wes and I wanted to thank everyone for attending this webinar. Here's our contact information if anyone needs to reach out to us. We will be responding to all questions that come in after this webinar, presumably early next week, maybe even tomorrow, and we can engage in email correspondence on an as-needed basis. Wes, do you have anything you want to add?
No, just thank you everyone for joining. It's humbling to think of the preparation that goes into putting on something like this. I certainly have a new appreciation for everyone who is putting out this kind of content.
Yes, agreed. Thank you, everybody.